Okay, now that we've learned the 4 circuit variables, hopefully you have those sort of internalized and memorized. We're going to derive the 2 equations that we'll be using a lot in this unit. One is known as Ohm's Law, and the other is the power equation. We already have one power equation. This is just sort of a twist on that to work a little bit better with our electrical variables. So when you're designing and building a circuit, there are only 2 things that you can really change. There's only 2 variables that you can really control. The first is the voltage, and the way you control the voltage is by controlling the battery. So each battery that you buy has a specific voltage that's determined by the specific chemical reaction inside it. If you look on any battery that you have at your house, you'll notice that it tells you exactly how many volts it is, and that's because it's basically telling you what kind of chemical reaction is happening inside. Most regular batteries are 1.5 volts, which means the chemical reaction inside them gives 1.5 joules of energy to every coulomb of electrons. I should say here that you can give partial energy. There's no reason those have to be whole numbers. Coulombs don't have to be whole numbers either, which you'll learn about more when you take more physics. But at any rate, the battery that you choose determines the voltage. So if you want more voltage in a circuit, the only ways to do it are to add more batteries, right? If you have a battery and all it can give you is 1.5 volts, but you need more than 1.5 volts, you need every electron to have more energy than that, you can add a second battery or a third battery. And this would be like going through 3 houses, and each house is like trick-or-treating. You get 1.5 joules of energy in the first house, and 1.5 joules of energy in the second house, and 1.5 in the third house. If you go through all 3, each electron is going to have 4.5 joules of energy, or 4.5 volts, by the time you're done. You could also replace those batteries with a different kind of battery. So those little button batteries that you see are lithium-ion batteries. They have a different chemical reaction inside them, and that chemical reaction gives a different amount of energy to each electron in a circuit. So those are the 2 ways you can control the voltage in a circuit. The second thing that you can control in the circuit is the resistance. Every device you put in a circuit has a natural amount of resistance, and the resistance of a device depends on the design. So the kinds of wires that are used, the kind of electronics that are inside it are going to determine the resistance of the device. If you want more resistance in your circuit, you can add those plain old resistors, or you can change the device that you have. A really common use for those plain old resistors is in a circuit that includes LED lights. You know, a long time ago, all we had were the incandescent lights, the standard light bulb that you kind of see pictures of online. Those light bulbs are really inefficient. So they've developed something known as an LED, which stands for light emitting diode, which is a lot more efficient. But you have to be careful because LEDs only want a very specific amount of energy, and if you give them too much energy, they actually burn out really quickly. So whenever you're designing a circuit that includes LEDs, you always put in a resistor, which basically sucks some of the energy out of the circuit before it can get to the LEDs. So it increases the overall resistance of the circuit, but then your LEDs won't burn out nearly as quickly. So given what we know about those 2 variables and the other 2 variables, we could assign them categories of independent and dependent variables. The voltage and the resistance are the independent variables. The values of voltage and resistance in a circuit or any part of a circuit depends on the hardware in the circuit. It depends on the devices that you've actually plugged in. And that means that changing one of those values doesn't change the other. If I add more batteries, it doesn't change my resistance, right? Because resistance depends on the bulb that I put in there. And if I change my light bulb or I add a resistor, that doesn't change the amount of energy that the battery is giving out. So those are independent variables, and the only way to change them is by changing the actual hardware. Current and power, however, are dependent variables. So the values of current and power are going to depend on the voltage and resistance values in the circuit. So if you want to change the current, the number of electrons flowing in your circuit every second, the way you do that is by changing the voltage or the resistance. Same thing with power. So the 2 equations that we're going to come up with in a minute are the equations for current and power. We're going to learn how changing voltage and resistance are going to impact the power and the current. So you start off with a plain old circuit. It's got a battery and it's got a light bulb. and you're not happy with the amount of current that's going through that light bulb, right? You want that light bulb to be, you want more electrons every second to be moving through the light bulb. The way you can adjust that current is by making changes to the voltage or changes to the resistance of the circuit. So I could change the voltage of that circuit by putting in more batteries, as we mentioned earlier. And if I put in more batteries, that means every electron is getting more energy. If you go back to your school day analogy, if you got more energy in the morning, that's going to make more electrons move through the circuit. They start moving a little bit faster. They get, they had that bowl of Wheaties and also a bowl of Captain Crunch in the morning. They got double dose of energy. They're really going to be moving through that circuit. A lot more electrons are going to choose to go through the circuit. So more batteries equals more voltage, and more voltage means that more electrons are going to decide to move through the circuit. In terms of relationships, this means that current has a direct relationship with the voltage. The more voltage, the more current you see as well. The other variable that impacts current, of course, is the resistance. So what would happen to the current if we replaced that resistor with a resistor that had a much higher resistance, so a much harder light bulb to get through without changing the voltage? So same battery we had in the first circuit, but this time the light bulb is a lot harder to get through. Hopefully it kind of makes sense and it's intuitive to you guys that the higher the resistance of the light bulb, the less electrons are going to be going through it every second. Okay, the harder the test is, the fewer students show up to take it. That's the big idea there. As far as relationships go, this means that current is going to have an indirect relationship with resistance. These two relationships can be combined into an equation that's known as Ohm's Law. You've seen Ohm before, of course. It has to do with the resistance of a circuit. It was a person that did a lot of work with circuits and developing these equations and got an equation named after them. So Ohm's Law basically says that current has a direct relationship with voltage and an indirect relationship with resistance. So please stop this slide for a second and derive the equation yourself, because once you've built it, you own it. So take a minute here. All right, two relationships comes up with one final equation. I is equal to V over R. You see that direct relationship with V on the top and the indirect relationship with R on the bottom. So this is Ohm's Law. It's a big important one. Put a big box around it. We'll be using it a whole lot. It's the equation that describes how current is impacted by voltage and resistance. The second equation we're going to derive for this unit has to do with electrical power. So we already know the equation for power. It's work over time, and you can actually get there. Get electrical power using that equation as well, but there's a little bit of a shortcut, so we're gonna do that because I think it'll save us some time throughout this unit. Remember that power is the change in energy every second. So in the school day analogy, the power is basically going to be the energy that's being poured out of the battery every second. So the battery is like the house. The house is giving energy to each electron, but the power is the total energy that it's giving every second. So that's basically going to be the energy for each electron and the number of electrons that go through, right? If you're thinking about this sort of as trick-or-treaters or something, it's the amount of candy every minute that comes out of your bucket. Or you can also think of power in the individual electrical devices as the amount of energy every second that is being transformed into some other sort of interesting, useful energy. The reason we care about power, and the reason why I said earlier that power was kind of the most important of the variables, is because the power is what determines how much energy is coming out of our devices. So if you have a more powerful light, it's brighter. If you have a more powerful speaker, it's louder. If you have a more powerful toaster, it's making more toast every second than a less powerful one. And often when we're using devices in electrical circuits, the goal is to get as much energy every second out of those devices as possible. So power is the variable that tells me how good a device is working. So if you wanted to calculate power, you wanted to increase the amount of power, the amount of energy every second that's coming out of your device, there's two ways to do it. The first is that we have more electrons flowing through the circuit, which is more current. We've already talked about how we can adjust current, so we could adjust current. The more electrons that move through the resistor, the more total energy is going to be deposited in that resistor, the more electrons that flow through the battery every second, the more energy that battery is going to be spitting out total. The second way to increase the amount of power is by increasing the energy that you give each electron, or the energy that each electron is using up. So if you have, a series of batteries so that each electron is getting more energy, each electron carries more energy through the circuit, that means that more energy is going to be deposited in each resistor. So there's two relationships here. Power has a direct relationship with current. It also has a direct relationship with voltage. So two direct relationships for power. Please take a second and figure out what that equation should look like. Hopefully you derived this equation. Power is equal to current times voltage. I should have done that little curly P power, but anyways, power is equal to current times voltage. Put a box around that one. That's the second equation we'll be using a whole lot in this unit. You can see the two direct relationships right there in the equation. Quick summary for this unit. Ohm's law and the power equation are the two equations that allow you to predict how changing one circuit variable impacts all the other variables. And the only two things you can actually change in a circuit are the resistors and the battery. The current and power are the dependent variables, and they depend on the changes that you make to those other two devices.